This video is for educational overview only. Viewers are encouraged to study the topic in detail and continue their academic learning alongside this video. Thanks.
Have you ever stopped to wonder what's actually holding our digital world together? What keeps it from just completely collapsing? Well, it isn't magic. It's a huge, fundamental shift in how we build things, a move from a really fragile old model to a much more resilient new one. So today, let's explore this revolution, from the absolute brink of system collapse all the way to the future of smart AI. To really get this, we've got to start with a crisis. We have to look at that terrifying moment when a system under extreme pressure doesn't just bend, it completely shatters. So picture this. It's April 2018. A startup is about to launch their first big feature. The whole company is buzzing. They send out the push notifications, they flip the switch, and boom, disaster. Alerts start lighting up like a Christmas tree. Services are crashing left and right. The team's biggest day just turned into a complete system-wide meltdown. What they just experienced, well, it has a name: the thundering herd problem. It's what happens when a massive flood of traffic hits a system all at once, totally overwhelming it and setting off a chain reaction of failures. It's a classic nightmare scenario in distributed systems, and it points to a really deep fundamental flaw in the architecture. So what is that fatal flaw? Well, it's an old way of building software, a way where every single part of the system is locked together in this incredibly fragile chain of requests. Let's walk through a super simple example. You go to place an order online. The order service calls the payment service and waits. The payment service then calls the fraud service, and it also waits. But what happens if that fraud service is just a little slow? Or worse, what if it fails? The entire chain just grinds to a halt. The whole thing is blocked. Your order fails not because there was anything wrong with your order, but because one single link in that chain broke. It's basically an old-school telephone call. System A calls System B and has to just sit there waiting on the line for B to answer and give a response. It can't do anything else, it's just stuck. And in a digital world that moves at the speed of light, being stuck is a death sentence. And this really gets to the heart of the difference. The old way is request and wait, it's blocking. You're literally stuck on hold. But the new way? It's publish and move on. It's non-blocking. You send your message out into the world and immediately get back to doing other important work. This isn't just some minor technical detail. It's a completely different philosophy. And this old telephone call model, it creates this absolutely brutal domino effect. A single failure can cascade and bring the whole system down. One slow service creates a massive traffic jam for everything behind it. Teams can't even update their own stuff without this huge, painful coordination effort with everyone else. It just totally undermines the entire promise of modern, agile software. Okay, so how do we fix this mess? We need a radical shift in our thinking. We need to build systems that don't just ask for information, but react to what's happening around them in real time. This is the big what-if question, right? What if, instead of constantly knocking on 1,000 different doors asking, hey, anything new? Anything new for me? Systems could just be notified the instant something important happens. What if they could just react? And that is the core idea behind event-driven architecture, or EDA. Services don't call each other directly anymore. Instead, one service, we call it a producer, simply announces that something happened, an event, like order created. Then, any other services that care, the consumers, are listening for those events and react when they see one. The key here is that they are completely decoupled. They don't even have to know the others exist. And when you put these two models side by side, the difference is it's night and day. We move from a pull model, where you're constantly begging for updates, to a push model, where the updates just come to you. We go from tight coupling to loose coupling, from systems that are incredibly vulnerable to those domino-like failures, to systems where failures are nicely isolated. On every single metric that matters for a modern app, scalability, resilience, real-time capability, the event-driven approach is just the clear winner. This all sounds amazing in theory, right? But how you actually build it? Well, you need a backbone. You need a central nervous system to handle all this data zipping around. And that's exactly where data streaming platforms come in. Seriously, think of them as the digital equivalent of a central nervous system. They're the connective tissue that reliably delivers all these event messages from the producers to all the right consumers, making sure nothing ever gets lost and that everything flows in real time. The undisputed king in this space, the de facto standard, is Apache Kafka. We're talking more than 150,000 organizations that rely on it, and it's for a good reason. Its design is just brilliant. It's built on this idea of a distributed, unchangeable log, which guarantees messages are never, ever lost and can even be replaced. It offers incredible resilience at a massive scale. This is not some niche tech. It is the engine powering the real-time world. But, as with any powerful technology, using it introduces some really fascinating challenges. Here's a big one, a crucial puzzle you have to solve. How do you guarantee that you both save an order to your database and publish that order-created event? Think about it. If one of those actions succeeds and the other fails, your whole system is now out of sync. This is a classic challenge known as the dual write problem. And the solution is so elegant. It's called the Outbox Pattern. Instead of trying to do two separate risky things at once, you only do one reliable thing. You write both the order data and the event message together in a special Outbox table inside your database, all within a single bulletproof transaction. Then, a totally separate process comes along, safely reads from that Outbox, and publishes the event. It's a brilliant way to use the database's own reliability to guarantee your events get sent every single time. You see, this new architecture isn't just about making today's systems more reliable. It's about building the foundation for tomorrow's intelligent applications. This is the key to unlocking the real potential of AI. Okay, so here's the big challenge for AI. To be truly smart, an agent needs context. It needs real-time information about the world around it. But you can't just open the fire hose and dump all of your company's data on it. I mean, that's a security nightmare, and it would completely overwhelm the system. The AI would literally drown in all that noise. And this is where event-driven architecture becomes a superpower for AI. Let's imagine an AI agent that manages a city's bus system. Most of the time, it's just watching high-level summary events. But then it sees an event for a delay on, say, Route 47. Instantly, it can dynamically subscribe to only the detailed granular event streams for that specific bus. It gets location pings, speed, passenger counts, traffic data, everything it needs to diagnose and solve the problem. And once it's fixed, it just unsubscribes. It literally zooms in on the exact context it needs, precisely when it needs it. So why is this such a game changer for AI? It means our AI agents get dynamic context without being overloaded. It allows intelligence to scale efficiently without boiling the ocean. And crucially, security is enforced by the platform itself, not by just hoping the AI behaves. It's what allows an AI to safely and securely tap into the real-time nervous system of an entire business. And all of this leaves us with one final, pretty big thought. For years and years, the goal in tech was always just to make our systems faster. But this shift we've talked about, it suggests something way more profound is happening. So I'll leave you with this question. Are our systems just getting faster, or are they finally learning how to adapt?